Okay, so I think we're recording this screen. I'm going to open up this. I'm going to do this. Okay, and I'm going to start the show. Okay, so thank you for your patience. I think one of the strategies here is I'll also just record this because it's always a little different every year. So I'm just going to summarize very briefly what we just talked about, and that is that we're talking about the advantages of going from the planar structure to the chair structure, and that in the planar structure, the bond angles here are 120. In going to the chair structure, the bond angles are around 111, so that's much closer to 109.5. The other advantage is if you look down any one of the carbons in the planar structure, you're going to find that the bonds are eclipsed, whereas if you look down on the chair, and I'm looking here at carbon that I've labeled 1 to 2, in fact, you can show that the bonds are staggered, and therefore we have a reduction in torsional strain. So that's a bit of a summary of what I just talked about. So I hope you see the advantage of having the chair. Now, what I'd like to do at this stage is to get you to start to think about, if you had to draw the chair, how would you go about doing it? And many times, like in a test situation, I'll likely draw it for you, and then I'll ask you to put stuff on. But I think in the assignment, for instance, I'll get you to draw it from scratch. So one of the things that I'd like to point out to you is that there's some symmetry in the chair. And what I'm going to do is highlight, for instance, these bonds right here. Okay? And you have some space just to the right. So I ask you to do this as well. So I'm drawing that and drawing that. And then with some luck, I'm going to be able to change my pen color. And I'd like you to notice that coming off on these sides, there are two parallel sets of bonds. So I can do this, and I can do this. Right? So the ones that are highlighted in purple, two parallel sets of bonds. And I know in the end, some of you are going to be much better than I am in making these drawings. Okay. And then the next thing I want to highlight is, in a sense, there's another kind of, oh, that's not what I want to do. There's another kind, that's not what I wanted to do either. Where are my pens? All right, there we go. They're down here. And I'm going to do this in green. So it's right here. This is another kind of pucker, if you will. And so that would be like this. So I would argue that you would start with this kind of V shape. You draw two parallel lines, and then you complete with another, in a sense, upside down V shape. And that should allow you to at least get started in producing this. And so maybe one of the things that you might start to notice in drawing the chair is, I say, there is some symmetry. And again, unfortunately, because I'm trying to show it all on the screen, maybe I'll just come back to my purple. You can see here, these purple lines are parallel to one another. And this red line right here is parallel to the green line right here. And this green line right here is running parallel to the other red line on the other side. So in a sense, there are a bunch of parallel lines. The other thing to notice is that off of each of the carbons, there are always two bonds. And I'd like you to take note of, for instance, let's say the 3 hydrogens here that are pointing upwards like that. Well, they're coming off of the carbons that are, in a sense, pointing upwards on my chair. And there are 3 hydrogens that are pointing downwards. And so they're coming off of the 3 hydrogens that are pointing downwards in my chair. These we refer to as axial hydrogens. So all of the ones that I've just drawn there are axial. And you can see that they sit along the vertical. Now we have a set of hydrogens that are equatorial. So on every carbon, they're axial and there are equatorial hydrogens. I'm going to draw one of the equatorial hydrogens right here. And in a sense, hopefully you see that the bond angle that's represented here will be roughly 109.5, or actually, I guess more accurately, 111. And it's not like we're going to get a protractor out and try to measure it directly, but you know, it's not going to be 90 degrees. It's going to be on the order of 111. The other sort of guiding thing is that this bond right here that I've just drawn, it's actually parallel to another bond. Can you see that I draw this? It's actually parallel to that bond and this bond. So it kind of guides you in drawing it. So for instance, now when I want to draw the next equatorial hydrogen, I'm going to draw this guy. And it's parallel to other bonds. So these bonds right here and these bonds right here. I'm going to draw another hydrogen that's equatorial. And that hydrogen, and I'll point to the folks that are here. So that bond right there is equatorial, is parallel to these bonds right here. I'm going to draw another equatorial hydrogen. And then lastly, actually I got 2 more. One here and one out there. So I would argue that perhaps that's one of the harder things to do, is to place the equatorial hydrogens, and we'll do a little bit more practice. But there is some symmetry going on here. Questions so far? So one of the things that we've done so far is we've established that going from the planar structure to the chair, there's improvement in angle strain, there's improvement in torsional strain. And then the next thing is we've practiced a little bit about how to actually draw the chair. So I'm taking some time here because, as I said, this can be tricky if the first time you go through this. So just at the bottom of page 95, I say highlight axial and equatorial hydrogens. So I'd like you to have some practice in doing this. So let's now draw 2 versions of the chair. Okay, we're going to draw the same thing. So I'm going to ask you to give it a try based on what I just showed you. Draw 2 of the same. Don't put the hydrogens on yet. So try, and just to kind of get you started, you may recall I did something like this. And this. And then you're going to draw 2 parallel lines. 2 parallel lines. And then you're going to draw another pucker or another V shape, but upside down, if you will, from the first V shape. So it would be something like this and something like that. Something like this and like that. And again, I know that some of your chairs are going to be much nicer than mine. I'm not entirely pleased with what I've just drawn, but it's good enough. Now you can see the title of this spot here is saying highlight axial and equatorial hydrogens. So let us in the upper structure draw in the axial. And here, let's draw in the equatorial. I want you to practice doing that. I want you to be able to see them. So I'm going to pause here for a second. On the upper part, draw the axials. Remember, those are the ones that line in the vertical. Oh, okay. Yeah. Oh, that's cool. Oh, that's a very good idea. Awesome. So in terms of the axial, again, I really want to emphasize that, you know, there's sort of an upper part of the chair and there's a lower part of the chair. And so in the upper part, carbons, and I guess you might say, well, what do you mean upper part? Well, I'd like you to get a sense, and if I could have eyes up just up here for a second, okay, that the chair, in a sense, does have a plane, if you will. And I don't want to make a big mess of it. Maybe I'll draw it right here on the left-hand side. There is a plane where there are those hydrogens that are, in a sense, slightly above the plane. Or pardon me, there are those carbons that are slightly above the plane, and then those carbons that are slightly below. And again, my line doesn't quite do it. All right, so you know, it's in this chair. Maybe I'm going to hold up a model. I know the people at home won't be able to see this, but planar, if I put it into the chair, there still is sort of the upper part and lower part. And the carbons that I'm showing you right here, that guy, that guy, that guy, they're upper, and so the axial will be pointing up. And the remaining carbons are down, if you will. So down, 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 as such. So those are the axial. And as I say, for every carbon, there'll also be the equatorial. And now in this case, what I'm going to do is to really highlight what's going on with the equatorial, I'm going to intentionally change that color to red and point out that there are two sets of equatorial bonds that are parallel to that. So that equatorial bond, you see how that's parallel to those red lines. And this would be parallel over here too. Right? So that guides you in being able to draw in those equatorial bonds. And let me change my color again. So let's say to purple. So I'm making that purple and making this purple. And in this case, it's this equatorial bond right here and this equatorial bond. Oh, I didn't draw that right. Pardon me. What do I want to do? No, that's not the right one. So that one, I want to draw that. They're parallel. And just give me a second here. The red ones, that's that one. That's that one. Okay, yeah, it's this guy. Sorry, wrong. No, purple. Oh, rats. Just give me a second here. Which one do I want to do? Ah, just choose that as the purple. That's in line with that guy. So there. This guy's purple. This guy's my purple. This guy, yeah, okay, there we go. So this guy's my purple here. And so indeed, it's this one as such, like that. Okay, and so that, I'm not quite getting the angle right. So let's do it here. So it'd be something like that. And then lastly, I think I'll just leave the other ones as black, but I'll highlight them a bit more. So we've got the black there and the black there. And in terms of the axial that would be parallel to that would be this one and this one. So you have the bonds to kind of guide you in how you want to draw or how you should be drawing those equatorials. Now, if it helps you to see, what's going on with these, well, then it's not a bad idea to put the hydrogens on. There we are. And over here, I'll put my hydrogens on. Questions about that? Okay, great. So we've established that on each of the carbons there are equatorial and axial, and that there are definite ways to be drawing them. Now, one of the things that we haven't talked about here is that you may recall when we were talking about the chain, and now I'm on page 96, there's constant rotation about the sigma bonds in the chain, and we have infinite number of conformers. We highlight 6 of the conformers, though. We highlight 3 of the eclipses and 3 of the staggers. In the rings, it's a bit different. So for instance, in the cyclobutane, you saw that there were 2 different kind of puckers. In the cyclopentane, there are actually a bunch of different envelopes. In the cyclohexane, there are 2 different conformers. And you need to be able to go from one conformer to the other. Okay. And this, at first, can be somewhat challenging. And you have to kind of keep your orientation, if you will. So one of the things that might be helpful for us to do is, again, I'm on page 96. I'm asking you to take this original conformer and let's number 1, 2, 3, 4, 5, 6. Now, again, the huge irony about this class is it's pretty visual, and I'm now going to be holding up a model for the purpose of the students here, but I've got an idea of how I can actually show it just on the screen. Okay, so I chose to use this really tiny model, which is unfortunate in the sense that it'd be nicer to use the bigger balls model, but the issue is that they're not so flexible, and when I try to show the change from one conformer to the next, things just sort of fall apart. So bear with me, and also everyone's way far from me, but that's okay. All right, so I hope that you can see that this essentially has the chair conformation. There's the seat, there's the headrest, there's the footrest. When this moves to the other conformer. Essentially, this is what happens. And it's helpful to think of it in stages. So that comes up like that. Right? So footrest comes up and now becomes, in a sense, what would have been, or what would be a headrest. And the headrest flips down, now become a footrest. So it's like, it's sort of the opposite chair. Not, in some ways, oh, it's just the mirror image. But it's not. It's one molecule switching from one conformer to the next. Now, there are transition states, but the molecule doesn't spend much time in these transition states. Now, what I want to highlight in doing this change, and I'm going to show, first of all, to you guys here, I'm also going to show a little video and all this sort of thing. I'm going to go back to the original, and let's focus on carbon number 4 that I've labeled on the diagram. And let's focus on this hydrogen right here, which is green in my structure. Okay. I hope you would agree with me that we can say that this hydrogen is equatorial. Right? Equatorial. Look what happens to that hydrogen when we adopt the new conformer. So again, I'm going to push this up like that, pull this down like that. So now this is carbon number 4. There's that hydrogen I was talking about. So carbon number 4 is now part of the footrest. The hydrogen that's originally equatorial has now become axial. Right? So whatever is originally equatorial will be axial. Whatever is originally axial will become equatorial. So I think what I'll do is before we go ahead and draw, I am going to grab this and pull it in here. And I want to draw your attention again to additional video resources. And we've got a bunch of different animations here. I'm going to go to the animation chair 2. And what we see here is the original chair. Now, it's not exactly how what I'm starting with, but it's showing the transition from one of the conformers. And, there are sort of transition points. There's the half chair, there's the twist boat, there's what's referred to as the boat. But none of them are generally as stable as the two different chairs. And so now another twist boat, half chair, and then to the next chair, or the other conformer, if you will. And I'm going to pause the video here just for a second. So similar to the little demonstration that I just did, in this animation, they've highlighted some of the hydrogens as being green. And the two structures are identical. So pay attention to, for instance, let's say this hydrogen, can I? No, I can't. This hydrogen right here, which is green, it's equatorial. And then watch what happens when we adjust the other chair to become the conformer. Okay, so sort of the transition, and now I'm going to pause. So you can see that the equatorial hydrogen now becomes an axial hydrogen. And I really encourage you, if you're having trouble picturing this, come and take a look at some of these animations, because they help you visualize what's going on. So with that in mind, let's try to do this. I see the internet has come back, but I think I'm just going to carry on. Okay, yeah. But we may have time for clicker questions, though. Okay, all right. So I now want to draw the other conformer. And you say, well, how am I going to do that? Well, you may remember that the first time we went to draw a conformer, we did this. And if I were to draw my lines now like that and like that, kind of parallel, well, I'd be drawing the same thing. So the approach now is to do this and that. So it's to draw them the other way. Maybe I can get a bit more of an angle on here. So I'm just going to do something like that and like that, draw them parallel. And then something like this. I'm going to number my carbons. So what was the footrest is now the headrest. 1. And one of the things that you really need to watch for is to make sure that you, like for instance, if I go along here, I'm going counterclockwise. 1, 2, 3. I got to go counterclockwise. 1, 2. Oh, okay. It's all good. I just need to stick this in for a second. I'm using it a lot today. All right. So you want to number and make sure that you go counterclockwise. And then start to fill in where the hydrogens are. So hopefully that charged it up a bit. So we got 3, 4, 5, 6. And then now put in all the hydrogens. Your axial hydrogens will be pointing up and down. I'm just going to move that number 4 away a little bit. So down like that. Didn't put my numbers in the right spot. So this is 4, this is 2. And then there's my other hydrogen. And then I'm going to put in my equatorial hydrogens. My equatorial hydrogens. My equatorial hydrogens. So there's another one right there. My equatorial hydrogens. There's a hydrogen here. A hydrogen here. And finally, a hydrogen coming out there. And note that I labeled this hydrogen on number 4. Where is it now? Yeah, good, good. Okay. Notice it was pointing downwards like that. Okay, so it's axial. So a common thing that I'll be asking you to do often is I'll give you a planar structure and ask you to translate that planar structure into the chair and to know where the different groups are. Or I could give you one conformer, and often I'll draw it for you, so you'll already have the template, and ask you to put where the other groups are in the conformer. Now I've been talking about groups. We haven't quite got to that yet. The substituents. So far we've just been focusing on hydrogens. So I'm going to pause here for a second. Are there any questions about what I'm illustrating to you? Okay, well then let's carry on. And yeah, let me see if I can open this up for the benefit of those that are here. So end show just for a second. We'll keep that because it does look like I do have the Wi-Fi. And I'll try to figure out what to do for the folks at home. Maybe I can do it as post it as a quiz or something. Oh, already in progress. Look at that. Resume. You guys ready? So just a second. Poll's not open yet. Look at that. Okay, select. All right. So this is the first check your understanding, number 6. Which of the following statements is true about the structure below? And I'm really hoping this is a very simple question for you. And for the 1, 2, 3, 4, 5, 6, almost got everybody in, and you're all correct. Look at that. That's awesome. Thank you for doing that so quickly. Okay, good. So of course that's the correct answer. And one of the things that, what this emphasizes in looking at this is often we don't draw in all the hydrogens. And if there are any atoms that are not hydrogen, then we're going to draw them in to show where they are. But, as I say, if we're going to draw in any hydrogens here, it might have been to draw that hydrogen here and this hydrogen here, just to show what the relationship is of those hydrogens to the groups that are already on. But we don't bother drawing the rest. It just gets really crowded and it doesn't really give us any additional information. Okay, so what we need to do at this stage is to start to talk about what happens when you have a substituent on the ring. And in teaching model number 7, I make the comment, conformers of monosubstituted cyclohexanes may not be of equal energy. So what I've drawn here is I have the two, or what will be the two conformers of methyl cyclohexane. And I've labeled carbon number 1 is where the methyl group will be. So you can see that the methyl group is here. Where will that methyl group be in the conformers? So here's the conformer. And again, this is not a mirror image, it's the conformer. So I've labeled where carbon number 1 is. It's down here, right? Okay, and it's the idea that, of course, this is axial here. Therefore, the methyl group in the conformer will be equatorial. It'll be there. The other thing to notice is, again, imagine that there's this sort of plane, and I'm sorry, my line's not going to look quite like a plane, but any group that is above the plane of the ring will be above the plane of the ring in both conformers. So that CH3 is above the plane of the ring. And it's clear in the first conformer, in that axial position pointing upwards. But in the second, in its conformer, the second conformer, this CH3 group right here, that is still above the plane of the ring. And you might say, well, how can that be? It's equatorial. Well, look at the alternative. The alternative is the hydrogen down there, right? So comparing this hydrogen to the CH3, the hydrogen is below the plane, the CH3 is above. Does that make sense? Okay, all right, good. Now, I'm saying that they may not be of equal energy. So far, when we drew the conformers before, like just of cyclohexane, both of them are of equal energy. But now let's compare these two. And we're just going to use this as an example to compare the energies. But the conclusion that we arrive at will apply to all ring structures, or to all cyclohexane rings. And one of the ways to do this is to draw a Newman projection. Now, I did give you a whole lot of room, but I don't think you need that much room. So what we're going to do is cite down carbons 1 to 2. So for the conformer on the left, if this is carbon number 1 that I'm highlighting, there's carbon number 1. My methyl group will be up here. And how about what we'll do here is we'll call this ring, let's say, associated with carbon number 2. And this will be ring associated with carbon number 6. So we're not going to draw up the whole ring, but we're just going to show where those things are. And looking down, so my eyeball, for instance, is going to be right here. It's going to look down carbon number 1. Looking down carbon number 1 to carbon number 2, I'd see a hydrogen here. and I would see the ring carbon number 2 there. No, I wouldn't. Try that again, Doig. I'm looking down carbons 1 to 2, and I would see, yeah, right, okay, not ring number 2, obviously. I'd see ring number 6. Please stop me if you're not seeing that. All right, so looking down here, ring 6 would be on that left. And at the back, of course, would be ring 2 carbon. And there'd be a hydrogen coming off of there, a hydrogen down here. And maybe what's throwing this off a little bit is I should call over here ring 2. So the rest of the ring structure. So I just didn't want to draw in the rest of the ring, but just to kind of differentiate. So that's one of the conformers. Now, if we draw the Newman projection for the second conformer, so I'll label over here ring 2. I'm going to label over here ring 6. Looking down, so my eyeball is looking down carbons 1 to 2. So initially I would see a hydrogen down here. I'd see a CH3 over here. I'd see a ring 6 over here. In terms of carbon number 2, I would see an H here. I'd see an H up here. And now the rest of the ring associated with carbon number 2 going to carbon number 3 would be down there. So those are the two Newman projections looking down carbons 1 to 2. Based on what we talked about last class, can we say that one is more stable than the other? They both have the same torsional strain, right? Because they're both staggered. They both have the same angle strain, if you will, because the bond angle is close to 111. What about steric strain? Do they both have the same steric strain? Which one has greater steric strain? Yeah, the one on the left, right? You've got more of the bigger groups closer to one another. You've got more steric strain. Whereas over here, the CH3 group is sandwiched between two hydrogens. Conclusion. Equatorial position is always more stable. I know I only give you one example here, but it could be demonstrated in general that the conformer that has the substituent in the equatorial will be more stable. And up until now, actually, when we've been talking about this ring, we've been talking about how when it adopts the chair, it has less angle strain and it has less torsional strain. We really don't talk about steric strain until you start talking about the substituents that are on the chair. Okay, so with that in mind, all right, so we've just come to this conclusion. What I want to show you is this beautiful chart on page 97. And it's showing if this is X in one of the conformers, and there's this X in the same molecule but a different conformer, the X on the left is axial, the X on the right is equatorial. And if that X is just hydrogen, well then both conformers would be equally stable. Look at what happens if the X is a methyl group. The conformer in the equatorial position is 20 times more common. Now understand, these are not resonance structures. This is an equilibrium. So the concentration, if you will, of the equatorial methyl group is 20 times greater than that of the axial. Look if it's an isopropyl or the tert-butyl. Right? That's an extreme example. And just to help you recall, remember that the tert-butyl, because I know Rick doesn't like common names, but I use common names all the time. Okay, so for the benefit of maybe others who don't know what I'm talking about, there's the tert-butyl group. Okay, all right, good. But now look at the halogens then. Remember how I said that even the methyl group will trump a halogen in terms of steric strain? The halogens here, yes, the equatorial is still more favorable, but not by that much. And you might have expected, for instance, there to be a trend. Fluorine, equatorial more favored, chlorine, and then bromine, and then you'd expect the iodine to be the most favored. And in terms of these different ratios, the iodine substituent is still favored in the equatorial position, but not quite as much as you might expect. And again, it has to do with bond distances. And as it turns out, even though the iodine atom is the largest, it's actually a little bit further out there, so it's not interacting as much. You don't need to know these ratios, but it's just to point out that even the methyl group has more steric strain than a halogen. And that the halogen's pattern is not what you might expect, but still the equatorial is more favored. So here's where we need to start to really get into some practice. And so I'm asking you to turn back to check your understanding number 7. This is not a clicker question, but rather I want you to translate this planar structure into the chair. And I'm also giving you another requirement. I'm looking for the most stable form. Now, I'll be honest with you, this is where I think it starts to get a bit challenging. So I really hope that we can nail this. So I'm going to give you a second to think about it. If you're going ahead, like certainly if you're working on a tablet, you can always erase. But if you're working on paper, you might want to do it first of all with a pencil, just in case you don't quite have it right the first time. Okay, now just to kind of set the stage here, note that my template has a bunch of hydrogens on there. So the idea is we're going to replace the hydrogens with the desired group. I say here, provide the most stable, lowest energy chair. And you've got 2 substituents. Which substituent should you focus on the most, at least initially? Yeah, because it's going to be the big bulky guy. Okay, good. The other thing I guess I want to highlight is in the planar structure, that is, again, what do those dashes mean? They're going backwards, right? So they're both groups, the bromol group and the tert-butyl are on the same side of the ring, and they're both going away from us. Does everyone see that? Yes? Brendan, you see that? Yes? All right, they're on the same side, and they're going away from us. They're below the plane, if you will. So where do I want to put that tert-butyl group? In other words, should it be axial or equatorial? Well, clearly I wanted equatorial, right? Now, sometimes when students see this, and one of the things I really encourage you to do is to number your planar structure and then number your chair. Now don't do this just yet, but what a student might do is they might do this. 1, 2, 3, 4. Because it just lines up nicely, right? Don't do that. Like you could, but I think you're making your life more difficult. Oh, actually, well, I want to I didn't finish my thought here. You can do that, but then what I don't want students to do is the following. So don't do this. 1, 2, 3, 4. It's okay to do the 1, 2, 3, 4 on the top, but don't do just what I just did here. This is what you're making your life more difficult. Why is that more difficult? Well, if this is carbon 1 and this is carbon 1, and recall that below the plane would be here, right? Carbon 1 below the plane. And what kind of group is this? Well, it's in the axial position. So is that going to put the tert-butyl in the axial position? Well, no. Now you could always then draw the other conformer so that it's in the equatorial, right? But why not go for what you really want to do the first time? So we don't have to number the chair sort of to match how I've numbered the planar structure. I can, start at a different carbon. So for instance, if I start here, let's say that's carbon 1, carbon 2, carbon 3, carbon 4. Right? So you can start at any spot. And in so doing then, if I put my tert-butyl group right here, that's carbon 1, and it's in an equatorial position, so that's good. And you have to make sure that you align up your carbons appropriately. So I'm going, for instance, here counterclockwise. So I'm going counterclockwise. And here I've got carbon 4. So where would my bromo group go? Help me out, guys, here. So I've established that tert-butyl is right here. Where does the bromo group? It goes on carbon 4, but where should I be drawing it? Is the bromo group going to be equatorial or axial?
It'll be axial.
It'll be axial. Because it's below the plane, right? And this hydrogen right here is above the plane. So in order to translate that planar structure, and especially the most stable, I'm going to initially focus on the tert-butyl, make sure it's equatorial, and now I'm going to put in the bromo group. And because both have to be below the plane of the ring, the bromo group, in this case, will be axial. I'm trying to read people's faces. Brian, is there something not quite sitting well? So, because on every carbon, there's an equatorial and axial, right? But in some cases, the axial is pointing upwards. In some cases, the axial is pointing downwards. So if the axial is pointing downwards, well then the equatorial, even though it seems like it's just equatorial, it's above the plane of the ring. The kind of, and unfortunately people watching this, at home won't be able to see, but, when I look at this guy, that equatorial is below the plane of the ring. That axial is above. This axial is below the plane of the ring. This equatorial is above. So both of these are equatorials. One's above and the other's below. Okay, and if I kind of just try to make this flat, that's above and that's below. Okay, all right. So again, this is probably the hardest part, but we'll try to do some more practice. But is that okay then? Yeah, okay. So what do you do when you got two substituents? And first of all, what I want to do is to make sure that we have some terminology for when we have two substituents. So right now I'm looking on page 97, and again, I sort of to emphasize, on the left-hand side, I have two substituents that are not hydrogen. They're on carbons 1 and 4. They're methyl groups. One is equatorial, the other is axial. But can you see that both of them are below the plane? They're both sort of underneath the ring. When they're on the same side of the ring, it didn't have to be underneath, but that just has to be on the same side, we say that they're cis. Now, of course, you have to have two things against which you can compare to come up with that conclusion. It's most easy if there's two of the same, and especially if you want to use this kind of like nomenclature. So you say cis 1,4-dimethylcyclohexane. If one group was a methyl and the other group's an ethyl, this terminology doesn't quite work so well. And there are other ways around it. For instance, if those carbons are chiral, well, then we can refer to R or S. But it's most easy if, of course, it's the same group against which you're comparing. Can you see in the structure that's on the right, we have a methyl and we have a methyl group again on carbons 1 and 4. And for the purpose of your notes, I would encourage you to actually draw a line like that so you can clearly see that the methyl groups are on opposite sides of the ring. We refer to that as a trans. But ironically, both of these substituents are equatorial. Okay? They're both on the plane. Now, or like, in the equator part, if you will. Are these conformers? Are they conformers? If they're conformers, all you need to do is allow that headrest to become the footrest and the footrest to become the headrest. No, they're not conformers. They're isomers. They're stereoisomers. The only way you can interconvert between them is to break bonds. Okay, so these are isomers. But I just wanted to show you those two examples. Do these isomers have conformers? Yes. You can take, for instance, the trans, and the trans will always have the methyl groups on opposite sides. The conformer to this, instead of the methyl groups both being equatorial, its conformer will have the methyl groups both in the what position? Axial, exactly. Whereas on the left, what was axial will be equatorial, and what was equatorial will become axial. But these are isomers, not conformers. So the next thing that I'd like to do is to just make sure that we're all on track about talking about cis and trans. So cis and trans can be applied to different groups, but it's a little bit harder in the nomenclature. So just coming over here, this is at the bottom, page 97. And what I'd like you to do is, and this is not a clicker question, just quickly go through and decide whether or not the groups that are present, the substituents, the things that are not hydrogen, whether they're cis or trans. No, okay. And again, when we first started this, we were drawing in all the hydrogens. I think you see the beauty, the advantage of not drawing in all the hydrogens and just focusing on where the action is. And again, trying to imagine that although we draw it as a chair, there is sort of this plane still. And so for A, Rachel, what do you think? Are they cis or trans?
Cis.
Excellent. Brendan, for B? Okay, so look on, let's say, this carbon and this carbon. And on the carbon that's more closest to us, you've got a methyl group and a hydrogen. So the methyl group, is it above or below the plane? Good, it's above. Good. All right, now look at the back, the carbon that's further away. Is that bromo group above or below the plane? Excellent. Is this cis or trans? Nice. Okay, excellent. Josh, C.
That one would also be trans.
Okay, nice. Okay, so that guy's trans. Brianna. Trans, beauty. Okay. So, and I can't draw a line so well for that one, but definitely that's trans. Okay, nicely done. All right, so to finish off, we have just a few more minutes. You guys are doing a great job. On the next page, and we'll spend the beginning part of Monday's class doing some practice, hopefully getting the folks that were not able to attend in person on track as well. So here now, I've got the two different isomers, but I've also drawn their conformers. And remember how we said, okay, if it's mono-substituted, it's always the equatorial that's more stable. But what if it's di-substituted or multi-substituted? How do we decide which conformer is more stable? So I'm not really comparing different isomers. I want to take a particular isomer, which I can label as cis or trans, and look at the conformer for that isomer, or conformers for that isomer, and decide which one's more stable, if possible. So first of all, let's look at the cis. And by the way, this is not a conclusion to be memorized. You pretty much have to do it on a case-by-case basis. And so what you may want to do is just do like a quick little label, like as simple as A and E and E and A. So recall, if the methyl group is axial in one conformer, it has to be equatorial in the other. So comparing these two conformers, can we say that one is more stable than the other? Both have an axial and an equatorial, right? And so, yeah, these are in equilibrium, and it would be, 50-50. The equilibrium constant would be 1, right? Product over reactant. But now, let's look at the trans. So we've got equatorial, we have axial, we have axial. I'm not being consistent in my labeling. I'll do this perhaps. And yes, these are in equilibrium, but can we say that one would be more favored? Yeah, okay, you get the idea. Okay. So I don't know the exact distribution, but this would be more stable. The equilibrium would lie on the left. You would have more of that versus the product, if you will. Now, don't memorize the conclusion, oh, trans is always going to be more stable. It depends. It depends on where the substituents are as to whether or not, where the equatorials will be. So we'll do more practice of this, and certainly when you start to look at the open OChem, you'll see that there's a bunch of practice related to that. So how are we for time? All right, do we have time for one last question? Yeah, how about one last question? We'll make this a clicker question. Just So you have two questions. So this is the check your understanding number 8. So which of the two following structures represent trans 1,3-dimethylcyclohexane? And the 6 people that are attending here, their answers are coming in fast and furious. Okay. All right. Well, oh, good. Look, I'm going to close the poll. And we end with one big histogram. Lovely. And just to highlight, and again, it depends. So you can see that actually these guys are in group 1 and 3. We have 2 equatorials, and there are hydrogens here like that and like that. So this guy's a cis. And then if we look at structure number 2, again, 1 and 3, we have here an equatorial and an axial. There's a and you see what I'm doing here? I'm drawing in my hydrogen just as a point of comparison. And I can see that the equatorial CH3 would be below the plane. The axial CH3 would be above. Indeed, this is trans. I hope it's pretty obvious that with these 2 axials on 1 and 3, that would be cis. And then finally, with number 1 and 4, so yeah, we'll call this 1 and we'll call this 4. And in this case, we've got an equatorial and an axial. But if I draw in my hydrogens, I can see that the equatorial and the axial are on the same side, so that would be cis. So indeed, folks have answered choice 2. So I appreciate your kind attention. I feel like I was a little bit distracted today by just having the whole Zoom thing go funny. So hopefully the lesson was at least somewhat coherent and you're feeling somewhat comfortable in working with these chairs. We'll do maybe 20-minute practice on Monday and move on to the next topic. See you, Brennan.